All right, we are going to begin the PowerPoint presentation for Chapter 19. It's going to give you a pretty good overview of Chapter 19, although there's a couple things that you'll need to look elsewhere to find out. Specifically, look at my presentation that I give on balancing oxidation reduction reactions. So with that, let us go ahead and begin our PowerPoint for Chapter 19. As you know, this one covers principles of chemical reactivity and very specifically for oxidation reduction reactions. There we go, there we're started. You can read through the chapter outline. Very specifically, we're going to spend a little bit of time on some commercial voltaic cells, but this part down here is probably what's going to be more important. For oxidation reduction reactions, definitely you want to look at the video I posted on balancing redox equations. Okay, just a little bit of a review. Electron transfer are called oxidation reduction or redox reactions. They can actually generate an electric current, so we can separate that out. We'll talk about that a little bit. And because we can produce electricity, this is the field of chemistry called electrochemistry. To review a couple terms, oxidation is loss of electrons, reduction, gain of electrons, and remember, losing electrons, oxidation, LEO, gaining electron reduction, GER. Now, the oxidizing agent is the one that was reduced, and the reducing agent is the one that's oxidized, just to make sure we have something confusing in this chapter. I tend not to pay much attention to oxidizing agent and reducing agents, but they are commonly referred to, so we'll have to actually learn those a little bit. Okay, just a quick review of assigning oxidation numbers. If we have a molecule, the oxidation number is going to be 0 because its charge is 0. If we have an ion, it is going to be equal to the charge of the ion. The oxidation number of atoms in uncombined elements is 0. Group 1A, 2A are both going to be +2, and fluorine is going to be a -1 in compounds. Hydrogen usually has an oxidation number of -1 in compounds. Yes, there are exceptions when it is a -1. Oxygen usually is -2. A couple exceptions to that are when it is combined with fluorine, that'll be OFF, or a little bit off there. It's also going to be a -1 in a peroxide. For example, H2O2. Hydrogen only has 2 electrons to give. It can't give 4, so oxygen can only be a -2. But that peroxide ion can appear other places too. There's also a superoxide ion where oxygen actually has a charge of a -1/2, but we won't see that much in this chapter. The most electronegative element in a compound takes its lowest oxidation number. This is probably the one that we need to pay attention to for other things. For example, if we have sulfur and nitrogen together, we're going to look at nitrogen and say it's got a lower or a higher electronegativity, so it's going to have its oxidation number of -3. Okay, couple definitions. We defined oxidation as losing electrons. Now, notice that if we lose electrons, that means it becomes more positive. The oxidation number goes up. Okay, reduction, we gain electrons, we have a decrease in the oxidation number. This is where the term reduction comes from. And then I mentioned oxidizing agent and reducing agent before. Now, when we take a look at electrons moving, it produces a current. It can run a motor or a light bulb or a number of other things. If we have a reaction to produce a current, it's called a voltaic cell, also known as a galvanic cell. And electrolysis is the opposite. We can actually force the electricity to go the other way, and we'll see a number of applications of that in some of the problems of the chapter. Okay. One of the common ones that we see, a very spontaneous reaction, if we take a piece of copper wire and we put it in a silver solution, eventually the silver is going to form and our copper is going to turn our solution blue. Okay, so the copper has gone from its solid state into the copper 2 state. meaning it had to have lost electrons. The silver goes from its state where it's in solution here to a state in which it has solid, it has gained an electron, now becomes silver solid. And we can write that overall reaction there. Copper goes from a 0 to a +2, meaning that copper has lost electrons. It's losing electrons, oxidation. The silver has gained electrons. Silver has been reduced. And we can occasionally, just if you want to draw what is called a bridge between the two that are undergoing changes. Sometimes this is a nice shortcut instead of rewriting everything. But for a lot of things, we're going to need to write the oxidation and reduction half reaction anyway. So we might as well go ahead and get started and write those. Now, when we're balancing oxidation reduction reactions, the book goes through a method, and they first talk about trial and error. Trial and error is really difficult, especially when you realize that you have to pay attention to charge balance and mass balance. So a systematic approach is going to be better. Your book the author of our book likes to separate it into half reactions, balance those first, and then combine them together. I think you'll find the writing the half reactions is going to be really important. It's going to allow us to do some other things here in a short amount of time. Now we add those two equations. The equations cancel, giving us 1. Now this was a simple one, fairly simple one to balance. Some of the more complicated ones that you'll see, you definitely want to look at the method that I show. Here is a summary of the book's method. You'll want to go and watch the video that I put up on balancing oxidation reduction reactions. That's linked here as well as on the Canvas site. Okay, now electric current, that is the motion of electrons external to our reaction. What we can do is we can separate into two half reactions. So our oxidation reduction reaction, in this case we have zinc giving us zinc plus, that's our oxidation. Copper 2+ going to copper, that's our reduction. Now, if we just put zinc and copper, that is going to happen, but there's going to be no useful electric current produced on there. So what we can do is we can separate it into two half cells. I can put zinc in a solution of zinc ions, copper in a solution of copper ions, add a salt bridge to give us a circuit, because if I don't have a complete circuit, electron can't flow. And then I can produce a wire between the two electrodes or pieces of metal, and electrons will flow through that wire. Okay, this is accomplished in a galvanic or voltaic cell, two different terms for the same thing. And if I put a group of these together, it's called a battery. All right. So some of the components, the salt bridge, a common one to use is sodium nitrate, potassium nitrate, ammonium nitrate is commonly used. There's a number of different salt bridges, compounds that we can use. These ions do not react, but they do move, okay? The anions go towards the anode, the cations go towards the cathode, and this helps us maintain a charge balance in our solutions as we are having oxidation and reduction occur. The negative electrode is known as the anode, a negative electrode, which is oxidation. Also AO, hey, those are my initials, AO. Okay, both begin with vowels. The cathode is a reduction or positive. You can remember the red cat. That is positive there. Both begins with consonants. And electrons go from the anode to the cathode. They go alphabetically. Okay. Here is a diagram of a cell. Here we have the copper-silver cell that is involved in here. In this one, copper is the anode, silver is the cathode. Now, you might remember that copper is not always the anode. Copper could be the anode or the cathode. It depends on what the other one is. And we'll look at how we can tell that later on. Okay, so here is our cathode reaction, which is a reduction, our anode reaction, which is the oxidation, and I combine those to get a net equation that we have. So what happens to the copper electrode? It's going to disappear. What's going to happen to the silver electrode? It's going to get bigger. Okay. All right, a little bit more. Each of the components is called a half cell. Electrodes are made of conducting material. So if we have something like hydrogen gas, it is not going to conduct electricity. So we would use something like platinum or possibly graphite. So if you see platinum or graphite in a cell, you'll realize they're not actually reacting. This is just a place for the electrons to flow. Okay. They're basically just a surface for electron exchange. So an electrochemical cell with copper and silver, we notice copper, negative, it's the anode. And when we hook it up to a voltmeter, if we get a positive voltage, we know the negative one is connected to the anode and the positive connected to the cathode. If you do it backwards, and you put the positive one with the copper and the negative one with the silver, it will read a negative voltage there. Flip your leads around, you'll be able to measure the positive reaction that is occurring. Okay, so again, here is the terminology. I'm not going to read this all, you can look at that. All right, the copper zinc cell, and I used this in the first lecture on chapter 19, is a very important one. It's sometimes called the Daniel cell, and it is a voltaic cell. The electrodes are placed in separate compartments, and the wire connects the electrodes with a salt bridge present. Now, the voltmeter measures what we call cell potential, but it also is called electromotive force, which is abbreviated EMF. The EMF and the capital E are the same thing. You'll see them used interchangeably. Your book actually uses both terms. If you're looking at different sources, you might see EMF, you might see E0, and I will tell you right now, the ACS exams will use both. On a test or a quiz, I may ask you for the EMF, I may ask you for E0, I may just ask you for the cell potential. Okay, the E with a little zero means that it's standard conditions. The E without the zero means it's just the cell potential. Now, the hydrogen electrode is what is used to compare everything. It's important because it's the reference for that. And here you see a picture of a hydrogen cell. Notice that metal that's in there is not hydrogen. The hydrogen is actually a gas. Okay. Here we have a voltaic cell in which hydrogen is reacting. Notice that we also have another reaction where iron 3 is being reduced to iron 2. And here I have another platinum electrode. So sometimes the reaction that occurs in solution does not give you a solid metal or consume a solid metal. In this case, your electrode would be inert. Okay. If I connect a copper and zinc cell, the zinc ends up being the anode, the copper ends up being the cathode, and I get a total cell potential of 1.10 volts. Okay. And for the zinc copper cell at 25 degrees Celsius, and when zinc and copper are at 1 molar solution. Now, I know you're realizing, wait a minute, if my reaction gives us more zinc ions and less copper ions, aren't these going to change over time? Yes, and so will the voltage change over time. Imagine that. Batteries don't just run forever, darn it. Okay, so for this zinc cell, the cell potential is 1.10 volts, and because it's at standard conditions, it is called the standard cell potential, which is the E with a little zero on there. If you're just measuring it, you're measuring E. If you're measuring it standard conditions, it's E0. Okay. Balanced half reactions can be added together. We have our overall reaction for a balanced equation. And if we know the electromotive force for each half reaction, we can find the cell potential for the entire net reaction. Generally, what happens is we take a look at the comparison of each of these to hydrogen. Hydrogen kind of gives us our ground level or our sea level. It is our basis for comparison. So when we look at potentials, if we measure everything against hydrogen, we can then compare them to each other. Okay, so for this reaction, and there's a shorthand notation that you probably ought to be familiar with. Zinc goes to zinc 2+. That's the oxidation. So we list that first. our element before and then our product. This is the concentration. Notice the zinc 2 plus is aqueous. Copper 2 plus is aqueous at 1 molar to copper solid. The 2 lines here represent a salt bridge. The 1 line here indicates that there is an electrode present, a phase boundary, or so between solid and liquid there. So if we wanted to show the shorthand for this one, here would be the shorthand notation for that one. And here I have hydrogen and iron. We could also write that one out. Now notice that our electrode in this one is platinum, and our element that is oxidized is hydrogen. So we write the electrode in there with our phase boundary. We put the pressure of hydrogen at 1 bar. Then we have the solution in its concentration. This is how we would do one of those. So if you start to see something like this, realize, oh, wait, the platinum is not reacting. It's just listed as the electrode there. Okay, so now it's time to talk about batteries a little bit. Now there's 2 kinds of batteries. There's batteries that once you use, they just go dead and you're done with them. We also have secondary batteries, which are called storage or rechargeable batteries. Okay, now the good old-fashioned Energizer, the A, or you probably don't see A's anymore, double A's or triple A's or C's or D batteries. Those are all primary batteries. They go dead, they're done. But we take a look at, for example, a lead storage battery, the one in your car. That's rechargeable. It might go dead, but then you can charge it back up. All right, now one of the first batteries that was used commonly was a dry cell battery. And here you have the anode and the cathode. And the reaction, you'll notice here, produces ammonia gas and hydrogen gas. Now this is, it can give you a fairly decent amount of electricity to use, but one of the problems is that we produce gases. They found out that it did a similar reaction to it in the alkaline state. We would have a product that doesn't have gases, less likely to explode. So this is known as an alkaline battery. This is the reaction that occurs in your common batteries that you put in your calculators, the AA's or AAA's. Here is the lead storage battery. It involves lead oxide and lead solid, and both are going to produce to give you lead sulfate. Now, in this particular case, both the oxidized and reduced elements are both lead. If I have that, it is called a disproportionation. That's not a really good name for it, but it's the name we have for it. If the same element is oxidized and reduced, it's called a disproportionation. We're not going to worry about that. Lead is one that commonly disproportionates. We get lead sulfate as our product. And if we get too much of it on there and it starts falling to the bottom, our battery loses capacity. This is why you don't want to run your car battery all the way down a bunch of times. You start losing some of that product there and you can't reverse it. Here is the 2 half reactions for the lead. Notice I go from lead to lead sulfate and lead oxide to lead sulfate. I then can add electricity and reverse those and charge it back up. Now notice this gives us a total of about 2 volts, about 2.04 volts. If you know that a car battery is 12 volts, how is that going to work? Well, that's simple. We put 6 of them together. Okay. Here is a nickel cadmium battery, also called a NiCad. I'll just let you look at that if you want to. You can read about that in the text if you want. There's also a section in your book on fuel cells, and this is generating electricity by hydrogen-oxygen fuel cells. They want to use hydrogen in tanks or generated from hydrogen, like for example, a hydrocarbon decomposition or something like that, and O2 is applied from the atmosphere. There's a lot of hope that this is going to help with our energy problems, but I think there's still a lot of things to work out with it. Obviously, we don't want to be walking or driving around with a tank full of pressurized hydrogen gas in there. That will be quite explosive, and the device that would take to contain that is going to be fairly heavy, definitely decreasing the efficiency of the vehicle. But there's some hope that we'll be able to come up with something from that. Here is an example of a hydrogen air fuel cell. And you can take a look at that. Now, there are a couple things that can produce hydrogen and store hydrogen that are a lot more dense. For example, there is a nickel metal hydride. We're using magnesium or lanthanum. Magnesium is a lot more common, so this would be more likely to be used. And it also is fairly dense. We can produce hydrogen from that. But again, this has not been perfected at all. This is something that some research is to be done on it. It could go somewhere. It could be a lot of our solution, or it could turn out to be nothing. We'll find out. In about 20 years, look back and see whether this was a very important thing or whether this was like, well, fortunately, we found this other thing that would help with that. Okay. So let's move on from the batteries and let's go back to some calculations that we're going to do. Standard electrochemical potentials. And different elements are going to give you different electrochemical voltages. What factors affect that? Well, it has a lot to do with the amount of attraction that the atoms have for the electrons, the ability to lose electrons, but we're not going to go through all that again. Just suffice it to know that different elements have different potentials. But how do we calculate that? Okay, so electromotive force that I was talking about is EMF. Electrons are thought to be driven or pushed, kind of like water is pushed by gravity. Okay, this force is produced by the difference in electrical potential between two electrodes. Okay, the unit is volts, and 1 volt is equal to 1 joule per coulomb. This will be important later on. Okay, the EMF is also, it can tell us something about the work that cell can produce. However, we're not going to go into that calculation right now. Now, the cell potential depends on the substances that make up the cell, the pressures if they're gases. That's why I don't like the book always uses E0 when it's talking about it. If it's not at 1 atmosphere for a gas, it's not a standard cell potential. It's just a cell potential. The concentration if they're solutions, again, if it's 1 molar, it's E0 or E naught. That's a little degree sign there, but I pronounce it E0. Temperature is also important. If we change the temperature, we're going to change the cell potential. Oh, that means that your battery is going to work different if it's hot or cold. Great. Yes, that's what that means. Okay. Standard conditions are those listed here. Standard potentials are measured against a hydrogen electrode, also known as the standard hydrogen electrode, G. Okay. Sorry, went too fast there. Okay, this is our standard hydrogen electrode. Its standard cell potential is 0 volts. Now notice it is a potential for a half reaction. This particular one and all others that are going to be listed in the table are reductions. We could put together a table of oxidations. However, the International Union of Pure and Applied Chemistry met and decided that they would go standard around the world and everybody list reduction potentials. Okay, so if I want to calculate the cell voltage, I could use those potentials. And if I know the potential for each of the reactions, if I know the potential for the oxidation and the potential for the reaction, I can calculate the standard potential for the cell. If I have hydrogen at the anode, copper at the cathode, it comes out fairly easily. My anode, it's going to have a cell potential of 0 because it's our standard cell potential. It's our standard hydrogen electrode. And just as its oxidation is listed as 0, its reduction is 0. Okay? Cathode's reduction in the overall reaction. This gives us a total of 0.34 volts. I can look up this one in the reduction potential table. Okay, so this is our sea level or our ground level that we use, the standard hydrogen electrode. Okay. Half reactions are written as reductions, again, because IUPAC said that. Oxidizing agents and the electrons are on the left side, and reducing agents on the right side. Okay. They're listed in order of decreasing standard reduction potential. Okay. And that's going to give us some useful information. If the cell potential is positive, it's product favored. If it's negative, it's reactant favored. And we'll talk about the relationship between the cell potential and delta G a little bit later on. Okay. The standard reduction potential, your book tells you to do the reduction of the cathode minus the reduction of the anode. I prefer to just change it to a reduction potential, oxidation potential, and just add them together. Okay. If we have values for the standard reduction at the cathode, we can calculate that. All right. So tables are in 19.1. There's also a table in the back of the book that has significantly more. And if we look at the table that's in the book, notice that we have increasing strength of oxidizing agent and increasing strength of reducing agent. So lithium metal is going to reduce things like crazy, okay? However, to reduce something, it's going to have to be oxidized. So if lithium goes to lithium plus electrons, it's oxidized. That's going to be a reverse of that if we write that out. Okay. The stronger oxidizing agents are written at the top. The stronger reducing agents are at the bottom right. So you can compare things to see whether something will reduce it or oxidize it by just looking at the table. Okay. So if I look at this, zinc can reduce hydrogen and copper, both. Copper can't reduce either one. All right, so let's take a look at the half cell for zinc. If zinc is on the negative, hydrogen on the positive, I end up with a cell potential of 0.76 volts. This would mean the oxidation potential for zinc is a 0.76 volts. Because of this, if I were to write the zinc in the reduction potential table, I would write the reduction of zinc 2 plus 2 electrons gives me zinc solid, which is a negative 0.76 volts. Because it's the opposite of that, or the oxidation, it is a positive 0.76 volts. Okay, now this is the negative electrode, also known as the anode, and it's what supplies the electrons. So the electrons are going to go from the zinc to the hydrogen in this place. Okay, oxidation at the anode, AO, red cat. So the overall cell potential is 0.76 volts. So the zinc for that, the oxidation is 0.76 volts, or the reduction potential is the opposite of that. So when we look this up in the table, we're not going to be able to find this oxidation. We will find the reduction, and we'll need to switch the sign. Just a simple reminder, if I get a positive cell potential, it's a spontaneous reaction. If I combine these together to get something that gives me a negative cell potential, it is not going to be spontaneous. And remember, we cannot combine two reductions. We have to have one oxidation and one reduction. Okay. So if I look at the copper versus zinc, go back to this one. The competition between the ions as oxidations is kind of like a tug of war of electrons. So if we want to see how they correspond to the activity series, if we look, copper is right here and zinc is down here. We see zinc is going to be able to reduce. It's a much stronger reducing agent. Copper is a stronger oxidizing agent. So the copper 2 is going to be the one that undergoes the reduction. Here's our spontaneous reaction. Now, some of you might find it easier, and I find it easier, just to list both reductions, write their values, and say, which one do I switch in order to find the overall positive cell potential? Okay. Copper is a strong oxidizer than zinc. Now, looking at non-standard conditions, and in case you're wondering, yes, in the class, the Zoom class, I will go through several different reactions and several examples of this. Now, the Nernst equation allows us to work under non-standard conditions. Here is the form of the Nernst equation here written in red, sorry. Okay, and if we see the cell potential, again, the real cell potential, not the standard cell potential, is equal to the standard potential from the cell. That's what we get by looking up things in the table and taking the reduction potential and oxidation potential and adding them together. That gives us the E0 of the cell. Minus RT over NF ln of Q. R is our ideal gas constant with the units of energy involved. T is our temperature. I shouldn't have to remind you, but I might as well. What do you think the units of temperature have to be? They have to be the same as R, plus the fact that we don't want to have negative temperatures. Okay. N is the number of moles of electrons transferred, and F is Faraday's constant. Now, you're probably wondering, Faraday, who is that guy? Well, this is Michael Faraday. He coined the terms cathode and anode, anion, cation, and electrode. He's known as the father of electrolysis. He also studied paramagnetism, electromagnetic induction, and he's one of the first to study benzene and other organic chemicals. Very important chemist in the history. And in case you're wondering, no, he didn't win the Nobel Prize because he lived before the Nobel Prize was instituted. Actually, I believe he lived before Alfred Nobel. Okay, now the common form is to take this and put in our R, take T at 298 Kelvin. N is still our number of electrons, which can vary quite often, but Faraday's a constant. So I have a constant here. If it's at standard temperature, I have a constant here, and there is a constant. I can just put all of those in there, and I get a negative 0.0257 over N ln of Q for that portion of the reaction. This is very commonly used. There is also a value, negative 0.0592 log Q. That's the one I learned because back when I was learning chemistry, our professors learned it where they had to use slide rules. I didn't have to use a slide rule, but we still use that form of the equation. Okay. Standard conditions remind you that solutes are at 1 molar, gaseous reactions are at 1 bar, and the cell potential measured under these conditions are called the E0 or standard electromotive force of the cell. Okay. So when we're at non-standard, okay, this one didn't work out very well. We'll just skip that slide. Okay, this is known as the Nernst equation. E is the potential under non-standard conditions. N is the number of electrons exchanged. Now, remember that's the least common multiple when we're balancing the equations, the least common multiple of electrons. Ln is the natural logarithm. So an example of a problem we could work is we could determine the voltage of a cell. We can measure it at 25 degrees. If I know the zinc, if I know the pressure of the hydrogen, I could find the concentration of my hydrogen ion in a particular cell. This isn't the reaction that's done in a pH electrode, but it's similar to that. We can actually use a reaction, an electrochemical reaction, to determine a concentration of something like the hydrogen electrode, okay, or the hydrogen ion. Now, going to the relationship between thermodynamics and cell potential, our reaction is written overall for that reaction. Delta G is going to be to negative N times F times E. Again, F is Faraday's constant, N is the number of electrons transferred, and E naught is the cell potential. So what this reminds us is that if E is positive, delta G is negative. If I get a positive E, spontaneous reaction. Okay. Another thing that we can do is we can actually do stoichiometry. Not only do electrons move, but we can measure the electrons that move. Current flow and time yields moles of electrons. So current is charge transferred over time, also known as coulombs per second. An amp is a coulomb per second. So if I know the amount of amps that flow, I can tell the amount of electrons that flow. And you're probably wondering, hey, AA and AAA batteries and C and D batteries are all the same reaction. What's the difference? Well, the difference is not in the cell potential. They all have the same cell potential. The difference is in the amount of current they're able to produce. Okay, so amps are coulombs per second. A Faraday is 96,500 coulombs per moles of electrons. Remember, Faraday's constant had two different sets of units that we're using. For this calculation, we'll want to use coulombs per mole. Okay, so if I had a 1.5 amp current pass through a silver solution for 15 minutes, how much silver metal can I get out of it? Well, let's take a look. Remember our current, this is I represents our current, is coulombs per second, okay? And if I have that current going for 15 minutes is gonna be, well, I need to convert from minutes to seconds, so I multiply by 60 seconds in a minute. And then I know that there are 1.5 coulombs per second. How do I know that? Because that's the amperage that we have here, coulombs per second. This would give me the total coulombs. I could then continue on. I tried to put all this in one step, but it didn't come out. So I broke it into two steps, but I would normally just write this all together. So 15 minutes times 60 seconds per 1 minute times 1.5 coulombs per second. Now, 1 mole of electrons is 96,500 coulombs. 1 mole of silver requires 1 mole of electrons. I know that because silver has a +1 charge. Ag plus E minus gives us Ag solid. If that number wasn't 1, for example, if I was doing copper 2 to copper 0, that would be 2 here, okay? And then multiply by the molar mass of silver, and I get 1.51. Yay, I can do stoichiometry again with this stuff. All right, with that, we have reached the end of chapter 19. Hopefully between this and the Zoom lectures, you'll have a good idea of what's going on. And with that, have a good day.